Hello and welcome to another lecture of classical motion of a single particle. I just continue the discussion which I started in the previous lecture. I introduce two small concepts which can be interesting. So, the first one is the concept of generalized momentum. Okay. So, we just note that when we write the kinetic energy T in the Cartesian coordinate system, it is given by half m x1 dot square plus x2 dot square plus x3 dot square. Okay. I am just writing instead of x y z x1, x2 and x3 in order to just get like accustomed to the summations. Okay. Okay. So, if you write this, you know that what is the momentum for this particle. So, this is the kinetic energy of a particle in 3D space. So, the linear momentum of the particle is simply given by P m x1 dot x cap x1 cap x2 dot x2 cap plus x3 dot x3 cap. Okay. And you can actually always show that this T actually can be operated by an operator which I can write like this r dot, okay, by giving this vector p. Okay. This operator is just like a gradient operator, but in velocity space. That means, this is nothing but del del x1 dot x1 cap plus del del x2 dot x2 cap plus del del x3 dot x3 cap. Okay. If you have this, then you can actually just operate this operator on half m x1 dot square plus x2 dot square plus x3 dot square. Okay. Yeah, I am sorry. Okay. And you will have simply is equal to. So, this will actually act on only on this by giving you m x1 dot x1 cap plus this one will give you m x2 dot x2 cap, and the third one gives m x3 dot x3 cap, which is nothing but p. Okay. So, if we know that from T I can have P just by just by operating T, okay, by a gradient operator, okay, which is defined in the velocity space, okay, we can actually say that in a very simple way del T del x I dot is equal to P I. Okay. This is nothing but the exactly the same thing here what I am writing here. Okay. That means, if I is 1, so you have actually del T del x1 dot is equal to P1. P1 is nothing but m x1 dot. Okay. You can also do this for I is equal to 2 and 3. Okay. Now, I can generalize this concept, okay, for the generalized coordinates and velocity by saying that I will call this quantity del T del q I dot, because now if you remember that I have already successfully expressed the kinetic energy T, okay, in terms of the generalized coordinates and generalized velocities. If I do that, then actually I can also calculate in principle this quantity del T del q I dot, and that will give me P I. This P I is known as generalized momentum corresponding to the generalized coordinate qi. Okay. Another concept is the concept of generalized force. For that we start by doing this calculating the virtual work. So, virtual work, if you remember, is given by delta Wi. Okay. So, I mean delta W actually, which is equal to F dot delta R, and this F dot delta R I have already defined in the last lecture. Okay. This is given by summation over del R del Q j delta Q j, there is no delta T, and j will be on the j will go from 1 to small n. Okay. And where n is the number of total generalized coordinates. Okay. You can then take f inside this bracket, inside this summation, which is done on the number of the degrees of freedom, effective degree of freedom. Okay. So, this, and you will have this j delta q j. So, instead of delta x, if you write delta q j, so the corresponding force like thing should be this quantity. Now, you see this quantity is actually, if I just call this capital Q j, then it is actually getting multiplied with delta Q j gives the total virtual work Q j delta Q j. Okay. This is known as generalized force. But of course, while just talking about generalized force, we are actually define this generalized force corresponding to the generalized coordinate q j. Now, in both cases you will actually see that we are just deriving a scalar, okay, both for generalized momentum and generalized force, whereas in general you know that force and momentum, they are in usual cases they are vectors, but here you will see for a system like one generalized coordinate can be like of the nature distance, another one can be of angle, then two momenta will not be of the same nature as well. One can be a linear momentum, another can be actually angular momentum. Okay. So, this type of thing. So, you can also understand that if one is force corresponding to some position type of generalized coordinate, then for angle like generalized coordinate it will be a torque, for example. Okay. So, you just think about that, and you will see that is why we do not really like define a vector for that, but we just define a scalar function corresponding to each generalized coordinate. Okay. Now, finally, in today's lecture I will derive the famous Euler-Lagrange equation, which I will denote EL, okay, in the rest of the course, and Euler-Lagrange equation is also known as the Lagrange's equation of second kind. Okay. And this actually creates an alternative way to obtain the Newton's equations of motion. Okay. The Newton's, for example, the equations of dynamics, that is F is equal to ma, without using the concept of force balancing, and you actually can avoid many a times for different non-trivial problems the drawing of free body diagrams. Okay. So, in this course we derive this for one single particle, okay, because this course is the classical motion of a single particle. This can be easily generalized for a system of n number of particles, more than one particles, okay, and also some systems which are not at all physical or classical mechanical system. Okay. So, this is very general, okay. The concept is very general. Okay. I just start with the kinetic energy of the particle of mass m. So, it is given by m by 2. Okay. So, summation over I x I dot square. Okay. So, we know that for every xi we will have an expression corresponding to its expression in terms of the generalized coordinates and generalized velocities, and that is why we can write now. So, 1 xi dot I can write as del xi del qk dot, okay, summation over qk, and there is of course a summation over I here, okay, yeah, and then you can actually write plus delta xi del t, del xi del t, okay, dot you can write summation over, here it is k, here you can write j, okay, del xi del qj dot plus del xi del t, okay. You can write that. Now, what you can do is that you can directly actually calculate. So, I will now say that I will now just directly calculate del t del qk, okay. I am just taking one specific generalized coordinate qk, and qk dot is the corresponding generalized velocity, okay. I am just evaluating del t del qk dot, okay. So, this is nothing but m summation over, so xi dot squares del del qk dot, okay, and that is why I will have m summation over I, okay, this can enter and it will actually have xi dot del xi dot del qk dot, okay. Now, if I have this, I can actually calculate this quantity separately, and I know that del del qk dot, okay, when I calculate xi dot. So, xi dot is once again is del xi del t plus summation over j, for example, okay, del xi del qk dot, okay, I am sorry, I should write j over here, yeah, j and j over here. So, you will see that these two commute. So, it will have del del t del xi del qk dot, okay, and then you will have plus, you will have two terms summation over j, one will be del 2 xi del qk dot del qj times qj dot plus you will have summation over j del xi del qj del qj dot del qk dot, okay. This first term would go to 0 because xi depends on, from our definition in the previous lecture, on the generalized coordinates and time only. So, just the partial differentiation with respect to generalized velocity would vanish. For the same reason, you can actually again use the permutation and make this thing vanish. The final thing will be simply, so here this is a quantity of, let us say, del q 1 dot del q 1 dot, you will have 1, and if you have del q 1 dot del q 2 dot, it will be 0. So, this is 1 when j is equal to k, it is 0 when j is not equal to k. So, this is a Kronecker delta. So, you can write this simply del xi del qj, okay, Kronecker delta jk, which simply gives you del xi del qk. Only when j is equal to k, this term survives, okay. So, that is something you can say. So, from this you can actually write finally del T del Q k dot is nothing but del x I del Q k, okay, which is this expression for this term, okay, times x I dot summation over I, and finally you multiply with m. Okay. Okay. So, this is something very interesting. Now, if I now do a DDT of this quantity, now we do DDT of del T del Q k dot. So, it is nothing but DDT of m summation over I del x I del Q k, okay, x I dot. Okay. That much I can say. Yeah. Now, if I have this, then I can say I will again have two possible terms. One is, so m summation over I DDT acting on del x I del Q k, okay, times x I dot, plus I will have m summation over I del x I del Q k x I double dot. Okay. That I can easily write, that is V I dot or x I double dot, the same thing. Okay. So, if I have this, I can then write for this first expression, I now again use blue. Now, again if I do DDT of del x I del Q k, okay, you will simply have first again. So, you just have to write del T of del x I del Q k, and then plus summation over again j is equal to 1 to n. Okay. So, del Q j del x I del Q k, okay, and then you will have Q j dot. Yeah, that much I can write. Okay. If I can write this, I can also write, so I can do some permutations and I can finally say, okay, this is del Q k del x I del T plus, again I can say here the permutation would become simply yes. So, summation over j 1 to n del x I del Q j dot. Okay. And finally, once again, if you see from, I mean if you see carefully, what is this? This is dx I dt. So, this is nothing but del Q k x I dot, okay, or you can write del V I del Q k, that is possible. Okay. So, finally, what we get? We get ddt of del T del Q k dot is actually equal to, so this part, okay, is actually equal to, there are two terms. So, one is this, so m, I have calculated this part, underlined parts. So, summation over I can actually write this summation here I, okay. So, I can say this is nothing but del V I del q k, okay, times V I, okay, because x I dot is V I, okay, plus del x I del q k, okay, x I double dot. Just I want to check once if this is correct. This is equal to m v I del V I del q k, that is true, and of course this is correct, yes, and then m del x I del q k, you have V I dot, correct. I can write again this one as V I dot, okay, without any problem. I can write that, yeah, V I dot, okay. Now, I am going to do something. So, you see that here all these things I can write this as V I dot, because these things are in Cartesian, okay, that is very important. Okay. So, now I will do something very interesting, that is I can recognize this one as nothing but, so del q k of summation over I m V I square by 2. So, this is nothing but del t del q k, okay. So, d dt del t del q k dot minus del t del q k is actually equal to m summation over I del x I del q k V I dot, okay. So, this is an important relation at this moment, okay. I now will do something a little bit strange, but this is a very useful mathematical technique. So, I can actually again write this as, this is nothing but m summation over I V I dot del x I del q k, okay. I will now do a multiplication on both sides with a virtual displacement delta q k, and I will make a summation on q k. So, multiplying delta q k on both sides and adding on k, we obtain d dt del t del q k dot minus del t del q k delta q k summation over k is equal to already m summation over I V I dot del x I del q k times delta q k, and then you make another summation over k, okay. I can do that, okay, without losing any generality mathematically. Now, I can say that this is, I can take this also here, summation over, so m k and I m, so V I dot, okay, del x I del q k delta q k. If you remember what is this, so if I just make an summation over k first, so what would it be? It will be simply m I m V I dot then summation over k del xi del qk delta qk. What is this? This is nothing but dxi. Okay. So, I am now just trying to say that, okay, so if this is true, just a minute, so it is delta. Now, this is the virtual displacement of xi, which is nothing but delta xi, correct. So, I will actually have m summation over I m v I dot delta xi. Okay. So, on one side I will have like this. I know D'Alembert's principle. Now, we recall D'Alembert's principle So, you see that D'Alembert's principle simply says that m r double dot minus f I okay, dot delta r is equal to 0, where this one is the force acting on the particle excluding any force of constraints. Okay. That is true. Okay. If I have this, I can actually check that here you have this V I summation over V I dot delta xi is nothing but m. I have made mistake over here. There are two m's everywhere, sorry for that. Yeah. So, here you will have m summation over I, it will be simply V. I now forget the summation, okay. It will be simply V dot delta r or m r double dot delta r. Okay. So, I have the whole equation is equal, whole expression is equal to m r double dot delta r. From D'Alembert's principle, I know m r double dot delta r is equal to simply f I dot delta r. I will replace it here exactly, and I will have this is equal to f I dot delta r. Okay. Now, the point is, there is a subtle point that if I think that this is something which can be written as a gradient of some scalar function v, I do not know what this is now. This is something very important here. I just use this one, although you can see in various books that they already started by saying that this one is a force and this one is a potential. I am simply saying here this one is the acceleration. From D'Alembert's principle, you have this one dot delta r is equal to f I dot delta r. You just put that f I is some force, I understand, no problem for that, and I write f I as gradient of v or minus gradient of v according to our convention. Okay. If I write that, actually you can show that this, so delta v will be actually equal to this f I dot delta r, okay, and will be equal to minus delta v del q k times delta q k. If you admit this part, then you see that ddt summation over k ddt of del t del q k dot minus del t del q k times delta q k plus del V del Q K delta Q K, okay, is equal to 0, where again I am writing this with a summation over here, summation over K, summation over K. Okay. I can now suppose, assuming del V, so V is a function whose only dependence is on Q's and T. Okay. Del V del Q K dot is equal to 0, we can write, okay, del V del Q K dot is equal to 0, and that is why you can say d dt of the whole thing is 0, and so I take the green color, you have K d dt of del T del Q K dot minus del T del Q K delta Q K, okay, plus summation K, okay. I have again minus, so I will do now use a minus sign over here, minus del d dt of del V del Q K dot minus del V del Q K is equal to 0, delta Q K. Okay. I can finally write, take a global summation K d dt of del Q K dot of T minus V T minus V, okay, minus, yes, minus del Q K of T minus V times delta Q K will be equal to 0. And the last step is, now since all the Q Ks are generalized coordinates, they are already chosen in such a manner that all the holonomic constants are used up. So, they are mutually independent. Even if you are talking of a constrained motion, for generalized coordinates they are independent of each other, and that is why every delta Q K can be arbitrarily varied from one another, and that makes the possibility of choosing every single coefficient multiplied to delta Q K, okay, to vanish. And so, for all k running from 1 to n, we have d dt of del L del Q K dot minus del L del Q K is equal to 0, where L is given by T minus V, V can be a function of Q and T. Okay. This one is known as Lagrangian of the system, and this one is known as the Euler-Lagrange equation or the Lagrange's equation of second kind. Okay. Thank you very much.